It's very quick. It's mostly that I think Andrew's idea of having a specification with the programs is a good one, but I would really like them to be in English, nothing formal, because how you turn it into something formal will depend on the tool. So I agree that it's nice to say, okay, this is the functional specification, but please make it English.
Michael, why don't you go?
Yes. So yeah, so do you see my slides?
Yep.
Okay, great. So hey everyone, thanks for coming. So I would just give a very brief introduction about RefinedC, which is kind of a tool we're developing here at the MPI SWS together with a few other people. For example, Peter Su's group, also Robert, for verifying C code on top of Iris, and kind of the yes. So I don't need to go into the kind of, I guess, the motivation for why we want to verify C code for this crowd, but I just want to say, like, kind of the big idea of RefinedC, or the kind of the big goal of RefinedC, is to kind of bridge the gap between kind of the two or between two pillars of like verification, which is on the one hand that one wants to, like, as we've seen before, like one wants to have like foundational proofs for C code, right? Like something in a proof assistant, which a proof assistant can check, and where you have some mechanized semantics of C, but also try to combine that with a high degree of automation. So something where maybe very fast, or more in the spirit of very fast, where you like write annotations in your C program and then you just run the tool, and in the ideal case it would automatically verify it. In practice, sometimes it works better, sometimes it doesn't work so well, but maybe we'll get there later. So so to achieve these two goals, let me say how RefinedC achieves these two goals. So for the foundational part, RefinedC is based on top of the Iris program logic embedded in the Cog proof assistant. So you kind of use your separation logic, a bit similar to VST and very fast, to reason about these C programs and generate these foundational proofs using Iris. And we can also use Cog as like the specification language, similar to like VST, and you can just define your mathematical model in Cog and proof lemmas about that there. And right, so for the automation part, the idea is to not kind of try to automate Iris or raw separation logic directly, but instead build a type system on top of Iris, and then kind of like inspired by Rust Belt, and then kind of build a proof search procedure, build the proof search procedure as some form of, can be viewed as some form of type checking for this type system. And and then one kind of writes in the source code, one writes kind of type annotations, and then uses kind of this type system to do the automatic proof search, to do the verification of the C code. And let me quickly talk about the two pillars of this type system, which is, on the one hand, it has ownership types, which are have been proven very useful in Rust, for example, to reason about pointers and memory management. So you can, like, ownership types allow you to express, okay, I now own this region of memory and I can kind of really manipulate it. And on the other hand, well, like in Rust, ownership types only prove safety of the program, but in RefinedC we want more. We also want to prove functional correctness. This is why RefinedC also provides refinement types, which allow one to actually express functional correctness specifications and also verify these functional correctness verifications using RefinedC. Right. So I also want to briefly show you a quick example of how RefinedC looks like, how it So here we have a simple allocator, which is just here you have like at the top right, you can see the state of the allocator. It's just some buffer with some length. Then you have an alloc function, which allocates from the structure. And yes, and like it checks. So this alloc function first checks if there's enough space available. If not, it returns null. Otherwise, it decrements the length and allocates from the end of this buffer. And yes, so how can we verify this with RefinedC? So in the interest of time, I'll go over this very briefly. If you're interested in more, I'm happy to chat with you later, or also, yeah, feel free to ask questions. But yes, so here, like the how this works in RefinedC is that you write your annotations as types. Here, for example, you specify the types of the arguments and the return value. And you can, for example, see here is an own pointer type, which kind of codes the, yeah, we say like this pointer we get as the argument as an own pointer type. So we exclusively own the state of the allocator, can freely manipulate it. And then we also return ownership of the allocated memory, which is kind of the separation logic, which is, yeah, the specification you expect from an allocator. But we also need to give back the ownership of this memT structure. So we need to add an ensures clause, and we need to link this ensures clause to the argument, which we can do with kind of a ghost parameter p here. We will say kind of this argument is the own pointer, points to the memory location p, and then in the ensures clause in the post condition, we give back ownership of the memT structure at this t. So this is kind of the ownership verification. Now we can also do functional correctness verification, where we can first introduce a few more parameters, like this parameter a, which says how many bytes are available from the allocator, and we can use that as the refinement of this memT structure. And we also can introduce a parameter for the allocation size. And then we can, for example, specify the exact condition when this allocation succeeds. Here succeeds if n is less than equal to a, so if the requested allocation size is less or equal to what's available from the allocator. We can also compute how much space is available in the memT structure after this. And now once you've written the specification, one can actually give this to so they're the refinement types to encode the functional correctness. So when one has written the specification, one can now give this to the RefinedC front end, or to RefinedC, and what it does is it takes kind of this code with the annotations and translates that into Coq. So like the code gets translated to like a deep embedding of C in Coq, and the annotations get turned into specifications and lemmas which prove that this function satisfies the specification. And then you can run the RefinedC type checker on this. And in this case, RefinedC can automatically verify this program. Right, and yes, for this program, this works well, but we have not also only verified small program, but like, so in this is the evaluation from the original RefinedC paper. We've verified a few smaller examples, also a bit inspired by what has been done in other tools. Some simple data structures or various forms of allocators. The most complicated examples we verified is this, on the one hand, this number 4, which is a hash map with linear probing, where you can actually see here in the second to last column, there's some form of pure reasoning, which tells you kind of, this is kind of the functional correctness proof about the model. And you can see, like, for the linear probing hash map, there's actually a lot of pure Coq reasoning involved to proving that actually the algorithm implemented by this C code, which just traverses an array, really behaves like a map. And otherwise we also verified the an allocator from the Hafnium hypervisor. Yes. So Not sure how I'm doing on time, but I want to also spend some time highlighting what I think worked well in RefinedC, or what I'm generally happy with, and what needs more improvement, or well, what are current limitations of RefinedC. So right, so one thing I'm quite happy with is like the general automation technique used by RefinedC, which is a form of logic programming for separation logic, which gives you kind of a nice predictable form of proof search, which is relatively efficient in Coq standards, but which you can also kind of interact with and debug. Also in general, kind of with separation logic and this proof automation, I feel like you can reason relatively nicely about like pointers and local variables. So like automating this ownership reasoning works quite well. Also there is we spent some time into kind of trying to adapt RefinedC to an relatively accurate C memory model, where like, well, it's hard to say what exactly is the right C memory model is, but like there we worked on kind of trying to integrate some version of PNVI, or some at least some model which we believe to be sound above the PNVI AEUDI model with RefinedC. Right, in general, also which is quite nice to have this workflow of like going like having the C code with the annotation and then translating that to Coq, and you for many tasks you can just modify the C code with its annotations. And also, yes, also in general, the idea of using a type system to specify your program, and works relatively well, I think. And you can kind of also, the foundations of using Iris as in the background means that you can easily extend, or yeah, like an expert can easily extend RefinedC with new types, and kind of this way kind of add new support for new coding patterns and so on, without needing to touch the core of the proof search procedure or so. And yes, of course, like foundational proofs are nice, and yeah, okay, well, RefinedC supports unstructured jumps, unstructured go-tos, but not sure how, I just want to say this for fun, not sure how relevant this actually is. Because RefinedC represents the program as a control flow graph. Right, then the other part, what could work better, or what doesn't work so well. So one very important thing is that RefinedC is a relatively young tool, and it has seen, I think, a lot less man-hours spent on it than like at least the other tools we've seen so far, like VeryFast and VST, and of course they're like RefinedC doesn't have such impressive case studies as these other tools, which like hopefully maybe it will get them at some point, but at this point this is something which RefinedC doesn't have, and this also means well, yeah, there's a lot more polishing to be done, and like evaluating and evaluating more, adapting it more. Yes. Right. Another thing which can also be annoying is still the amount of annotations in the source code. Like we've seen before for the simple allocator example, actually the specification we put above it was, I think, as many lines as the actual implementation of the code. And yeah, we currently actually, so this is something we're currently looking into by trying to infer the annotations and specifications for the C code using by abduction, or yeah, using ideas from by abduction. Another thing which is very nice in VST, of course, is the connection to ComSert, and like in general that you can transport your proofs to assembly code, which is something which RefinedC doesn't have at the moment, but this is also something we're looking into, maybe trying to do some form of translation validation or so for connecting the result of RefinedC to some assembly code, but this is still relatively early. Right, another thing is performance. which is like especially annoying for like if you have like an interactive tool where like you just put annotations in the source code and then you have fully automatic proof search, and then RefinedC sometimes takes like yeah, for larger examples it can take like minutes to actually give you back a result for your function. And yeah, this is yeah, like this is something which we would like to improve, but it's also tricky because like doing foundational proofs in Coq tends to be not so super fast, especially if you're doing large proof terms and stuff like that. Right, then the error messages at the moment, or generally the user interface, is more geared towards expert users who kind of know how the type system works and how it internally how the proof state works. But yeah, it's can be hard for kind of new users or people not so familiar with the internals to actually get to understand what's going on. So like, for example, there's nothing as fancy as like very fast interactive debugger thing. And right, some more like, so yeah, so RefinedC so far we focused on verification of on automating the separation logic aspects of the reasoning. We had this we had Lithium, we had this separation logic programming based automation technique, but we haven't focused so much on pure side conditions. And so there you sometimes also still need to do manual proofs, or you often need to do manual proofs when you don't do non-trivial stuff, and would be nice to integrate with like, I don't know, SMT solvers, whatever, more automated stuff for proving pure stuff more automatically. Right, and yes, so there's also some stuff in C which is either just not implemented yet, or which is kind of a bit tricky to support. I think the most important ones are RefinedC doesn't support floating point numbers, doesn't support strings, but I'm not sure, that might be mostly a front end thing, I'm not sure. And there are two things where I'm aware of where the RefinedC, like the C semantics used by RefinedC is unsound, which is the first one is block scope local variables. Right, so I should say for both of these, the front end does an over approximation and warns if your code might fall into a fragment where you hit this unsoundness, but like the core thing is I don't think is sound. So like if you have, first thing is block scope local variables. If you have a variable in a block and you do a go to inside that block or out of that has some weird semantics in C, which is not captured, and also sequence points. The sequence point stuff is not implemented in RefinedC. Yes, so these are the I think that's, oh yeah, right. Right, so also there's still a lot of documentation and tutorials and stuff like missing. So yes, so for example, like this software foundations volume and stuff in VST is like very nice to have stuff like that, but yeah, for RefinedC, there's a lot less at this point. Yes, so these are the main points I have, and yeah, I guess like we can. Are there any questions about this?
Okay, great. Thanks very much. Questions, comments, thoughts?
So you talk about performance. So the type checking happens in Coq. So it's not like the front end performs the type checking.
No, the type checking happens in Coq. So the type checking, like this Lithium, this automation, or the automation is implemented as a tactic in Coq, which directly generates a proof term.
I see.
So yeah, it would be nice to make or it would be an idea to kind of do that in a separate process and then somehow generate the proof term separately. But at the moment, this is not.
On that, I should know the answer to this. I don't know how much arithmetic is going on in that type checking.
Sorry, how much arithmetic? Yeah, well, that depends a lot on what you're doing. But RefinedC, like we are the type system, it tries to kind of separate the pure side condition, which contain like the arithmetic stuff usually, from the kind of main path of the type checking, which checks your local variables and so on. So the arithmetic usually there's some things with, if you do really weird stuff with arrays sometimes, or with integer pointer cast, there's some arithmetic going on, but usually it's kind of moved, like it's not in the main path of the type checking.
How much concurrency stuff do you currently do in RefinedC?
Yes, this is a very good question. So we do some very limited concurrency stuff. So in the original verification, we've verified kind of very like small C programs doing like a spin lock and a one-time barrier. We've since verified a ticket lock implementation, which so kind of, but automating concurrent stuff is a lot more tricky, or open research problem. So so there we haven't gone much into this direction. And for this more complicated ticket lock, there it's also kind of using the fact that you can interleave RefinedC automation with like manual proof steps. But we haven't looked much into concurrency. Also, I should say this is using a sequentially, it's using a C semantics with sequential consistent excesses and non-atomics, but there's no relaxed or stuff like that going on.
Okay.
Abbreviated at the start, but maybe we should try and regain our schedule and switch to Gregory.
You guys hear me?
Yeah.